High performance computing. Introduction to high performance computing. So you could see here, yes, just some images which shows about the high performance computing. And yes, the evolution of high performance computing, the early era of supercomputing, and the high performance computing systems, and the major vendors, and a performance. It's like speaking about this high performance computing, the early era of supercomputing. Maybe it's from the 1975 to 1995. So that era started to be the early of supercomputing. And these high performance computing systems were generally custom built specifically for the system workloads. And the major vendors included the Cray, the CDC, the NHC, Fujitsu, and the Thinking Machines. And these systems delivered very high performance, but the glitches, it's like at the extremely high cost. Okay, and the performance was also far superior to standard commercial commodity computers at that particular time. And speaking about the role of early microprocessors, so they were single chip, the general purpose microprocessors. It's like were invented in the early 1970s. And what kind of a drawbacks they had is they lacked the performance needed for scientific supercomputing. That was the big drawback they had. And but in the late 1980s, right, from 1970s, the late 1980s, the microprocessors became powerful enough. Microprocessors became stronger enough to enter into the high performance computing market. And the emergence of cluster computing became a huge factor. And it came out in the late 1990s. And by the end of 1990s, this clusters made from workstations or PC hardwares. So it's like the clusters which are made from the PC hardwares. It's like became very much competitive. They became very competitive. And these clusters, what they did is they matched or exceeded traditional supercomputers. So it's like this cluster computers. So what they did, they matched or exceeded traditional supercomputers in theoretical peak performance. So the what happened is the cost effectiveness became a major advantage over custom supercomputers. And this speaking about the modern HPC landscape. In nowadays, that is probably today, they are dominated by off the shelf, that is a kind of commodity hardware. So this process used in HPC are not primarily designed for scientific computing. Okay, they are not exactly designed for scientific computing, but they are adapted for it. That is, they can be adapted for it. So this commodity clusters provide a high performance to cost ratio. Yes, and the current role of the traditional supercomputer vendors, the small number of traditional vendors nowadays generally operate in niche markets. Okay, and also they are designed systems which are to be optimized for high single CPU performance and large scale parallel workloads. Okay, and these systems are used only when application requirement exceeds the commodity solution. So when that comes into the picture, these kind of application requirements comes out. And when you see the typical path for scientists and engineers, so most use the commodity based high performance clusters. Okay, and the migration to specialized hardware is only when the demand grows, depends on the demand definitely. And we have the vector computers. And speaking about the vector computers, this vector process supports a programming model which is well suited to scientific computation. Definitely, it's kind of a programming model. And despite their advantages, vector computers have become rare in modern HPC environments. Yes, and you could see this is the structure which you could see has a vector coprocessor, and which is a part of also the memory system. And yes, this is how the stored program computer architecture concept, the von Neumann architecture, considered as a backbone. Okay, one of the oldest architectures. It's pretty simple. So as you can make out in the figure, it has a CPU, memory, and the input-output unit. And in the CPU, it has the control unit and the ALU, the arithmetic logic unit. Okay, and that is being integrated with the memory. And speaking about this one Neumann architecture, it's continuous instruction and a data flow architecture. The instructions and data must be continuously supplied. It's like it needs a continuous supply. Which one needs a continuous supply of instruction and data is the control unit CU and arithmetic logic unit ALU. So these places are heavy demand on the memory interfaces. Okay, memory interface plays an important factor. And the next is the one human bottleneck. There are some bottlenecks. There were some bottlenecks. Definitely speed, the limited speed of data transfer between memory and CPU. Yes, that was one big bottleneck. The limited speed of data transfer between memory and CPU. And once when this limited speed comes out, what it does is it restricts the overall performance. And yes, this performance limitation, as there is a restriction, is known as a von Neumann bottleneck. And considerably it was one of the most severe constraints. Yes, it's a kind of a very important constraint in traditional computer architectures. One Neumann bottleneck, and you could see this is just the one Neumann bottleneck, how it looks off, which probably with the driving logic and with the distributed memory. And there were some mitigation techniques like the architectural optimizations, the programming techniques. Okay, and speaking about the architectural optimizations, that is the cache, the pipeline, the prefetching, and these things were there. And these help reduce the impact, like the architectural optimizations, like the caches, the pipelining, the caches, pipelining, and the prefetching. And coming into the programming techniques, like this data locality, that stuff, this loop optimization, controlling the number of loops. Also, even though they were trying to use it as a mitigation techniques, but it's alleviate the bottleneck. Okay, despite these improvements, the bottlenecks, even though they were there, the bottlenecks cannot be fully eliminated. Like these were all the trying parameters. And speaking about the sequential nature of the architecture, the architecture process, how it processes a single instruction at a time. Yes, it works on only with a single instruction at a time and on a single data element or small group of operands. Okay, either through a single data element or small group of operands. And the execution is inherently sequential. It goes ahead with sequential. And the SISD model. This model is comparatively a kind of an architecture. It is single instruction, single data. That is how it works. It works. It's kind of single instruction and parallel with the single data. So this SISD, what it does is it represents the traditional sequential execution model. It's a kind of sequential. And towards parallelism, that here the parallelism came into the picture, like to support the parallel execution. Okay, so these are some of the key focus in modern HPC systems. And speaking about the general purpose cache based microprocessor architecture, the complexity of microprocessors. So these microprocessors are among the most complex machines. Initially, they were kind of considered to be very complex, but despite this complexity, they are based on the stored program digital computer. Yes, they work on the stored program digital computer concept, and the complete understanding of all the internal details is not required. It's like it doesn't, what to say, it did not require a complete understanding of the internal details. The functionality is sufficient. And what are the need for high level understanding? It's like it for the performance bottlenecks, the limitations in computation and memory access. So all this forms the need for high level understanding. And once when these things are satisfied, what we can do is we can focus on how data and instructions flow. Okay, so it's like, but we don't get an exact information on transistor level, right? We don't get that. But we can focus on how this data and instructions could flow, right? That is what we can see. And speaking about the overall CPU organization, a modern CPU, there it has some components: the execution units, yes, the registers, the load store units, the instruction queues, and the cache memory. So these are the components which a modern CPU has. As you all know, all things are very important: the execution units, registers, the load store units, the instruction queues, the cache memory. And speaking about the chip area, they are mostly dedicated to support data movement, not computation. And next is the execution unit. So under the execution unit, this ALU, this arithmetic unit, performs actual computation. There are some important units inside this. The floating point unit, it's called as a FP, which is used for the floating point operations. And when you want to perform this integer operations, it is INT. Okay, so these are the two things. So these units occupy only a small fraction of the chip area, right? It doesn't occupy much space, so they occupies only a small fraction of the chip area. And what they do is they execute arithmetic and logical operations. Like the main thing is they execute this arithmetic and logical operations. Yeah, that is what it is being used. And the CPU registers. Speaking about the CPU registers, the register stores operands with negligible access delay. Right. So the access delay is not a big factor. It's a negligible access delay. And the CPU registers are typically divided into two kinds. One is for the floating point registers for the floating point operation, and one is integer for the general purpose registers for the floating point operation and for general purpose. And this modern process will have 16 to 128 user visible registers. That is how the ranging it goes. It goes to 16 to 128. And in some architectures, it's like all arithmetic operands must reside in registers, right? So all these things should happen inside a register. And yes, as you could see, this is the typical block diagram of how a cache-based microprocessor. It's a single core. It's one core. This is a block diagram of how it looks. So you could see here from the main memory, you have the integrations with the memory interface and the L2 unverified, unified. Sorry, it's unified cache. And you have the instruction cache and the data cache. You have the integer and the floating point and the memory cube, right? You could see it's being differentiated for the floating point and integer registers, right? So these are the operations. You could see LD, load, SD, the store, right? Add, multiply, okay, for the floating point. All these things forms a combination of a typical cache-based microprocessor. And speaking about the performance metrics and benchmarks, it's like all these components of the CPU core. What it can do is it can operate at the what is it kind of some maximum speed, and that maximum speed is being called as a peak performance, right? And this limit can be reached with a specific application on many factors. And what we do is here we introduce some basic metrics. That is, it can quantify the speed of a CPU, the scientific computing leads to the centric to floating point, usually with double precision. Yes. And what you could make out is, yes, this is the data centric memory hierarchy of how it is being placed. So it's like, yes, you could see the DRAM gap in the leftmost figure. So this DRAM gap denotes the large discrepancy. Like there is a bit of discrepancy definitely between the main memory and the cache bandwidths. So it's like this model must be mapped to the data access requirements of an application. Depending on an application, this has to be fixed out. And the floating point performance, how it is being measured is in flops. That is how the floating point performance is measured. The performance of floating point unit is measured in floating point operation. That is flops, as I said. It's floating point operations per second, flops. And the primary operations, what it does is the floating point addition and the floating point multiplication. These are the very primary floating point primary operations: the floating point addition and the floating point multiplication. So these operations generally where it is being used is for the scientific and engineering computations. Yeah, there might come a question like why this complex arithmetic is not counted. Okay, so it's like yes, the operations such as division, the square root, and the trigonometric functions comes out as operations, and these are not being included in flops because it's like the share execution is a big question mark. So it's like the share execution resources with add multiply units a big question mark. And also the next one is they execute much more slowly. Yeah, so the execution is pretty much slow, so their contribution to overall performance is negligible in practice. Yes. So this is how the peak, what to say, the complex arithmetic is not included. So this high performance software, what it actually should do is it should minimize the use of such operations. So the division, the square root, and the trigonometric functions should generally be minimized. These kind of operations. And this floating point capability of modern CPUs, that's like what they can do is they can typically produce 2 to 4 double precision results per clock cycle. And with clock speed, imagine the clock speed is 2 to 3 gigahertz. Okay, and it reaches the peak performance, the peak core, 4 to 12 gigaflops. It can reach over there, 4 to 12 gigaflops. And the data supply to arithmetic units is one important factor, that is feeding the floating point units with operands is complex and performance critical. Yes, so that is one big thing. Feeding the floating point units is complex, definitely complex, and the performance depends heavily on how fast data can be delivered. So the important things which comes into the picture is the memory bandwidth, the data transfer between the cache memory and the main memory, and also it is measured in gigabytes. Yeah, gigabytes per second, GBs. And the memory bandwidth, yes, that is one big bottleneck when the performance comes. The memory bandwidth can become the main performance bottleneck. And the key performance metrics, there are two key performance metrics. One is the G flops per second, that is the computational capability. The other one is the GBs, the data movement and the capability. And when we see something with the data centric view of performance, that is from a performance aware programmer's perspective. So how do we see this? It's like the computation is defined by the data movement and data reuse, and also the algorithms manipulate data. It's like definitely, but the execution is limited by hardware bandwidth. And the importance of low-level benchmarking. The low-level benchmarks are used to understand the peak floating point performance. Definitely, it is used to understand that. And also the next one is memory bandwidth. Okay, why these things are considered is it's like this benchmarks. What they do is they help programmers to identify and optimize where exactly this performance bottlenecks are affected. Okay, so when we set these benchmarks, it becomes easy for them. And yes, this is a small code fragment of a vector triad benchmark, like how this performance measurement is being done. You could see some initial examples of the basic code fragment. And yes, coming into the vector triad benchmark, right? It's a commonly used benchmark to evaluate memory. And this structure of the vector triad, how it works is it works on a nested loop structure. Yes, you have this nested loop, and the inner loop, the innermost loop in a nested loop. What this inner loop will do is it will perform one floating point multiply and floating point add. That is what the inner loop will perform. And the final operation form is it is a of I is equal to b of I plus e of I into d of I. Okay, and yes, we have this three input vectors. You have the B, C, and D. So what this three input vectors will do is it will produce one output vector, which is A, right? So that is how the operation form works. And the purpose of the benchmark is, why do you have this benchmark? It measures the performance of data transfers where between the main memory, the cache, and the arithmetic unit, right? And it's like the memory access pattern. It's definitely based on the inner loop. So it's like three load streams. That is, you have the B, C, and D. These are the three load streams, and one store stream where exactly it is being stored, the output, right? It is A. So this is how the memory access pattern works. And yes, there is definitely a sometimes a need for an outer loop. Yeah, when you have an inner loop, we need an outer loop. So it's like an outer loop, what it will do is it will repeat the vector triad r times. That is what the main functionality of the outer loop. It will repeat the vector triad r times, okay, for the precise timing. And choosing the repetition count r is selected based on n. Okay, so the main goal is to keep overall execution time approximately constant across the different n values, okay, preventing the compiler optimization. And without precautions, the compiler may detect that the outer loop is redundant, yes, and it may eliminate it entirely. Okay, so at the time, a conditional call, a subroutine is included, kind of a dummy subroutine is included. And this role of the dummy call, like what it will do is it will make the compiler assume that the array contents may change between iterations. And also, like what it will do is it will prevent the removal of the outer loop. Okay, so sometimes this condition is always false, so the real no kind of performance penalty occurs. And yes, the performance metric calculation, it's like how the performance metric calculation, yes, the benchmark. So it's like the benchmark computes mflops, million floating point operations per second. That's what it's being called here, the mflops. So the calculation is based on total operations performed. Yes, two things. One is the total operations performed, and one is total execution time. Okay, so those are the two things which will be calculated, and the time measurement in benchmarking. Yes, the time measurement in benchmarking. So it's like the wall clock time. The wall clock time is considered to be the elapsed time. Okay, and sometimes this CPU time can be misleading due to this input output operations, the context switches, and other system activities. And where this kind of a problem is predominantly seen as in the case of parallel programs. Okay, there it is exactly. I mean, widely seen. And yes, this is a C routine of a wall clock time. Okay, on the get time of day POSIX function. Okay, the routine can be used in the similar way. You could see this get time of a day a POSIX function is being used. So this is how under the Windows OS. And the observations and the benchmarking insights, uh, the Fortran and the C compatibility, sorry, so the kind of older stuff. So the Fortran computers, it's like the Fortran compilers append a trailing underscore. So the providing functions with and without underscore, right? So that can be done, ensures correct linking. And what it does is it allows interoperability between Fortran and C programs. And also, what it led us to the performance of small loop sizes. That is a very small loop lengths, right? So very small loop lengths, which shows poor performance. And this kind of a behavior is common across where you can say this as this cache based microprocessors and vector process. Okay, so this behavior is common for the small loop sizes. And the performance trend on cache bed microprocessors, the performance increases with loop length, yes, yeah, and it reaches a maximum value. Okay, so once when it reaches a maximum value, it is followed by a sudden performance drop. Yeah, some kind of performance drops also occurs. This performance stabilizes for very large loops. When the problem comes for the very large loops, these kind of things come into the picture. And yes, so the performance increases with loop-in, reaches a maximum value, followed by sometimes a sudden drops in the power stabilizers for very large loops. And speaking about the performance trend on process, this low performance region extends to large n values. Yes, this extends to definitely large n values, and no sudden breakdowns are being observed. So the performance is pretty smooth. Right? The performance is smoother and more predictable. And the comparison of algorithms, this vector process and cache-based CPUs are complementary. Each performs well in different application domains. Yeah, so they have a good performance in different application domains. The code optimization. This proper optimization can avoid low performance regions, and the role of low level benchmarks, useful for understanding basic hardware capabilities. Yeah, and it cannot reliably predict performance for a real time application. The predictability definitely goes down. And the importance of application benchmarks, yes, it's best suited for evaluating suitability of a system when you want to understand the suitability. And also it uses realistic input parameters like matching production workloads. And where it is essential is it's essential for the system procurement. Yes, whenever we go ahead for a system procurement, so this application benchmark forms a very vital factor. And also when we want to compute a grand proposal, when you want to go ahead for the big or good grand proposal, this benchmarks application benchmarks plays a very vital role. And the limitations of standard benchmarks, like this benchmarks looks like spec, it's a rough guidance, it's not a complete guidance. And it should not replace application specific benchmarking. Yeah, definitely it shouldn't be done. It shouldn't replace this application specific benchmarking. So this could be some limitations of standard benchmarks. Thank you.